Have you ever found yourself wondering about the intricate nature of atoms and the universe? Where do electrons get energy to spin around an atom's nucleus? How did the first atom form? Do atoms ever actually touch each other? Are two atoms of the same element identical? Does an atom have a color? Why don't protons repel each other out of the nucleus? How big is a proton? If atoms are mostly empty space, how can things be solid? Why do atoms form molecules? Is a neutron star just one giant atom? What if the universe is an atom? What happens to your atoms after you die? Do atoms last forever? Let's delve into these intriguing questions to uncover some fascinating insights. An atom is most effectively envisioned as a compact, dense nucleus encircled by rapidly moving, orbiting electrons. This concept naturally raises a question. How do electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with a considerable mass, surrounded by tiny, negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system with a dense nucleus, the Sun, orbited by smaller particles, the planets. However, this model posed two significant issues. Firstly, charged particles that accelerate emit electromagnetic radiation. Since electrons are charged and accelerate during their orbits, they should emit radiation, which would cause them to lose energy and quickly spiral inward to collide with the nucleus. However, atoms are known to exist for much longer than a picosecond, making this model untenable. Secondly, atoms were observed to emit radiation at specific discrete frequencies, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom could not occupy just any orbit, but were confined to specific, quantized distances from the nucleus. He also proposed that there was a minimum distance an electron could reach, beyond which it could not move any closer to the nucleus. Bohr's ideas were not mere conjecture, they were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade earlier. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by a constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus, asserting that the smallest possible orbit of an electron would have an angular momentum equivalent to exactly 1 Planck constant. Higher orbits could have integer multiples of the Planck constant, such as twice or 3 times its value, but never fractions like 1.3 or 2.6. The full comprehension of why electrons possess specific orbits and well-defined energy levels required the complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can equally visualize it as a wave enveloping the nucleus. Waves confined within a limited space must adhere to special rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This is analogous to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave encircling a nucleus must fit the available space, and the nearest orbit is determined by the first standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying a smaller space. However, an entirely different approach to understanding this situation does not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around a nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, the electron possesses kinetic energy, trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its kinetic and potential energies, is negative. Consequently, adding energy to the atom is necessary to remove the electron. This concept parallels the behavior of planets orbiting the Sun. To remove a planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling toward the nucleus due to the attractive electric charge. However, because of the principles of quantum mechanics, the electron can never reach the nucleus, becoming perpetually stuck in orbit. Nevertheless, this situation is permissible according to physics, because the total energy of the system is negative, signifying its stability and binding the components together to form a long-lasting atom. You and everything around you are composed of countless atoms, estimated to be more than 10 quadrillion vigintillion in the observable universe, one followed by 78 zeros. Atoms are tiny particles consisting of electrons, protons and neutrons, which are, in turn, made up of quarks. The origin of these particles that make up atoms can be traced back to the Big Bang. The Big Bang theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. However, the process was much more complex than this brief explanation. To understand the scientific perspective of the Big Bang, we need to examine the events in the early universe. Unfortunately, we don't have a definitive understanding of precisely when the universe started, or if it indeed did. Our best model, the standard model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t equals 1. The theory predicts a singularity, a moment of infinite density, where all matter and energy were compressed into an infinitely small point. Most physicists believe this prediction may not be entirely accurate. We can only go back to 1 Planck time, which is about 10 to the power of minus 43 seconds. Before this moment, we have no knowledge of what occurred. So while we get very close to the beginning, it's not precisely at t equals 1. Understanding the events at this incredibly small timescale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales. This first epoch of the universe, known as the Planck epoch, occurred at 10 to the power of minus 43 seconds. During this time, it is believed that all the fundamental forces, including electromagnetism, the weak force, the strong force, and gravity, were unified as one grand unified force. To create a timeline of the Big Bang theory, we start before the Planck epoch, setting the clock to 0 at this point. However, it's important to note that this isn't exactly t equals 1, as we want to avoid the singularity. The state of the universe during this epoch and what happened before it remain unknown. The earliest time we can theorize about is the period of inflation, which occurred from about 10 to the power of minus 36 seconds to about 10 to the power of minus 33 seconds after the Big Bang. During this time, whatever existed prior to inflation experienced rapid exponential expansion, faster than the speed of light. This is permissible because there's no theoretical restriction on the speed at which space can expand. It expanded from a point to about the size of a large orange. You might wonder how this is possible since we know that nothing can travel faster than the speed of light. While that's true for information transfer, cosmic inflation involves the expansion of space itself, allowing distant points to move away from each other faster than light can travel between them. Most of our current understanding comes from the period after inflation. So, the accurate way to view the Big Bang is not as a single point of origin, but as a period when the early universe was extremely hot, dense, and rapidly expanding. Thus, the Big Bang is a description of everything that occurred after t equals 1. Inflation is believed to have occurred from 10 to the power of minus 36 to about 10 to the power of minus 33 seconds. The energy source behind this rapid expansion remains unknown, and cosmic inflation erases any information about what existed before it. The theory of the standard model of cosmology is well understood, starting at about 10 to the power of minus 12 seconds, as the universe's energy levels can be reproduced in current particle accelerators. Before this time, we can only speculate about the events. From about 10 to the power of minus 33 seconds to 10 to the power of minus 12 seconds, the forces of gravity, strong force, and electromagnetic and weak forces, collectively known as the electroweak force, were still unified. The origin of the initial massless fundamental particles is uncertain. They might have condensed from the energies present during the Big Bang, or an inflation field containing inflations could have decayed into the fundamental particles we observe today. Around 10 to the power of minus 11 seconds, the temperature drops further to about 10 to the power of 15 Kelvin, marking the beginning of the quark epoch. The electromagnetic and weak forces begin to separate, leading to electro-weak symmetry breaking. The Higgs field gains a non-zero potential, imparting mass to fundamental particles in the Standard Model. At this point, the essential components for atoms are in place, and the universe's temperature is around 1 quadrillion Kelvin. As the universe continues to expand and cool, the extremely high temperatures prevent quarks from combining into hadrons like protons and neutrons. However, as the temperature drops to around 1 trillion Kelvin at 10 to the power of minus 5 seconds, the quark plasma transitions into a hadron gas consisting of protons, neutrons, and certain mesons, which eventually decay into photons and electrons. As the temperature further decreases, particles and antiparticles begin to annihilate, resulting in lighter particle-antiparticle pairs, such as neutrinos and photons. Interestingly, there's a slight asymmetry in this process, with more particles being generated than antiparticles, leading to the survival of certain quarks and electrons. This enables the formation of protons, neutrons, and electrons, which are essential for creating the initial atoms. The annihilation process culminates with the lepton epoch, which occurs around the 1 second mark, when temperatures subside to approximately 5 billion Kelvin. During this epoch, leptons conclude the annihilation process. Following this remarkable display, the majority of matter particles transform into photons and neutrinos. However, due to the matter-antimatter asymmetry, a small quantity of protons, neutrons, and electrons remain, serving as the fundamental building blocks for atoms. At around a few minutes after the universe's inception, the epoch of Big Bang nucleosynthesis, BBN, begins, with protons and neutrons produced in equal numbers. Free neutrons are inherently unstable and undergo beta decay, transforming into protons over approximately 10 to the power of minus 15 minutes. As the temperature remains high, proton-neutron conversion is balanced with neutron-proton conversion. But as the universe cools further, neutron decay becomes more prevalent. Free neutrons strive to join other hadrons and form more extensive nuclei before decaying, leading to the universe consisting of about 75% hydrogen nuclei and 25% helium-4 nuclei, along with small amounts of deuterium, helium-3, and trace quantities of lithium-9 nuclei. During this period, the environment predominantly consists of ionized nuclei without bound electrons. The formation of stable neutral atoms requires electrons to attach to positively charged nucleons to achieve charge balance. However, the universe is still scorching, and electrons can only briefly adhere to nucleons before being forcefully separated due to their immense energy. As a result, the universe remains opaque, and photons carrying light continuously interact with nucleons and electrons, hindering their free propagation through space. This photon epoch lasts for about 380,000 years, until the universe cools down to 3000 Kelvin. At this point, electrons possess significantly reduced energy, allowing the electromagnetic force to permanently bind them to nucleons, leading to the formation of stable neutral atoms in a process called recombination. As a consequence, photons are no longer confined amidst the chaos of positive nucleons and negative electrons. They are now free to traverse the universe, and if we were present in space, we would be able to observe this light. Today, the first light of the universe, known as the cosmic microwave background, or CMB, can be perceived in all directions. This light was emitted during the formation of the first stable neutral atoms, providing us with valuable insights into the early universe and the origin of atoms. Atoms constantly interact. However, to comprehend this, we must first determine the definition of interact. Our typical understanding of interaction is based on the macroscopic world. I place a cup on the table. The cup interacts with the table. You dip your toes in the water. You interact with the water and so forth. In all these instances, one solid boundary or surface, the cup's bottom, the edge of your toe, interacts with another solid boundary or surface, the table's top, the ocean's surface. Nevertheless, our macroscopic understanding becomes less applicable at the microscopic level, which leads to confusion about interactions. If we could magnify the scale to the atomic level, we would witness a chaotic environment. Atoms and molecules are consistently in motion, colliding, twisting and spinning, resulting in a tumultuous scenario. However, one thing becomes evident. Atoms lack a definite boundary. There exists a nucleus, a collection of protons and neutrons at the center, surrounded by clouds of probability that indicate the potential locations of orbiting electrons. The principles of quantum mechanics allow us to calculate these probabilities, which extend throughout the entire universe. Nevertheless, in nearly all observations, electrons remain securely bound near the nucleus, so unless we are conducting high-energy collider experiments, we don't have to worry too much about it. Since atoms lack a firm surface, in a way, there's no tangible touch, because there's never a direct meeting of boundaries. However, touch also implies a close and influential interaction, and in that sense, atoms are in constant contact. Atoms interact due to the electromagnetic force, which arises from the electric charges of electrons and protons within them. Technically, this force has an infinite range, but it becomes significant only when atoms are sufficiently close. At times, atoms literally repel each other due to the electromagnetic force between their electrons. In that brief moment, it's challenging to describe their interaction as anything but touching. Even if the interaction isn't momentary, it still qualifies as touching. For instance, when we examine the cup on the table at the atomic and molecular level, we notice that the electrons at the cup's outer edge are repelled by the electrons on the table's outer edge. Despite the gap between the layers of electrons, which typically exists, the atoms are close enough to significantly influence each other. This is evident from the fact that the cup doesn't fall through the table, and the electromagnetic forces between the atoms counteract gravity's pull on the cup. At the macroscopic scale, when we say two objects are touching, it reflects the same interaction at the microscopic level. Atoms can also touch through other means, as the electromagnetic force isn't always repulsive. When atoms get close, the van der Waals force, a manifestation of the electromagnetic force, can lead to bonding between atoms. This process results in the formation of molecules, where the atoms inside them are definitely in contact. Lastly, even nuclei within atoms can touch, although it's extremely difficult due to the strong electromagnetic repulsion between the positively charged protons in each nucleus. Yet quantum mechanics plays a role here too. If two atoms are brought close enough and maintained for a sufficient time, occasionally and randomly, their nuclei can intermingle. This phenomenon leads to nuclear fusion, where two separate atoms merge into a single, larger atom. If the atoms involved are lighter than iron, the fusion process releases energy. It is through this mechanism that all stars, including our Sun, generate their power. Indeed, two atoms of the same chemical element are typically not indistinguishable. Firstly, electrons in an atom can occupy a range of possible states. Therefore, two atoms of the same element can be different if their electrons occupy different states. For example, one copper atom with an electron in an excited state, and another copper atom with all electrons in the ground state are distinct. The excited copper atom will emit light when the electron returns to the ground state, while the copper atom in the ground state will not. The nature of the chemical bonding experienced by an atom depends on the states of its electrons, so two atoms of the same element can react differently if they are in different states. Chemists are well aware of this fact, and to fully describe and predict a reaction, it is necessary to specify the ionization, excitation states of the electrons in the atoms. Additionally, even when left alone, an atom often does not have an equal number of protons and electrons. However, even if two atoms of the same element have their electrons in the same states, they are still not identical. For instance, they could be traveling or rotating at different speeds, which influences their ability to chemically bond. Slower-moving atoms, such as those in solid iron, have time to form stable bonds, whereas faster-moving atoms, like those in liquid iron, cannot establish such stable bonds. As a result, a slow-moving tin atom behaves differently from a rapidly-moving tin atom. But what if two atoms of the same element both have their electrons in the same states, and the atoms are both traveling and rotating at the same speed? Then are they indistinguishable? No. Although two such atoms are essentially chemically identical, they will chemically react in the same way. They are not entirely identical. Beyond the electrons, there's also the nucleus to consider. An atom's nucleus contains tightly bonded neutrons and protons. The same chemical element can have a different number of neutrons and still be the same element. These atoms with different numbers of neutrons are referred to as isotopes. While the particular isotope involved does not impact an atom's chemical reactions, it does determine how the atom behaves in nuclear reactions. Radioactive decay, the most common nuclear reaction on Earth, varies among different isotopes. Some isotopes decay rapidly into other elements and emit radiation, while others do not. For carbon dating, the fact that a carbon-12 atom is not the same as a carbon-14 atom is crucial to the dating process. Simply counting the number of carbon atoms in a sample will not provide information about the sample's age. Instead, you have to count the number of different isotopes of carbon. But what if two atoms are of the same element, have electrons in the same state, are traveling and rotating at the same speed, and have the same number of neutrons? Then are they indistinguishable? No. Just like the electrons, the neutrons and protons in the nucleus can exist in various excited states. Additionally, the nucleus as a whole can rotate and vibrate at different speeds. Hence, even if all else is identical, two gold atoms can have their nuclei in different excited states and behave differently in nuclear reactions. In summary, achieving two atoms of the same element to be perfectly identical is exceedingly difficult. In fact, such an accomplishment would be Nobel Prize-worthy. Nevertheless, it's important to note that atoms do not possess individual identities beyond what has been mentioned here. If two carbon atoms are in the exact same molecular, atomic, electronic, and nuclear states, then those two carbon atoms are identical, regardless of their origin or past history. Everything has color. Since nearly everything possesses a color, atoms, as the fundamental building blocks of reality, should also have a color, or does it? When you aggregate numerous atoms together, you obtain the screen that you are currently observing, which undoubtedly has color. So, does that imply that each individual atom has its own color as well? If so, is it the nucleus, or maybe the electrons that are painted? And if so, which color? The colors you perceive are a creation of the human brain. They don't genuinely exist outside of your visual perception. So then, what precisely is color? To understand that, you need to comprehend the nature of light. Light consists of photons, which are particles. However, this behavior is only evident when observed. Otherwise, they tend to act as electromagnetic waves. This phenomenon is known as the wave-particle duality concept. And yes, it is peculiar. These waves possess specific frequencies, and depending on their frequency, they are classified into 7 primary wavelength sections, ranging from radio waves with wavelengths the size of Earth to gamma rays, the size of atoms. The human eye can solely perceive this small section known as visible light, while everything else remains invisible. You might wonder why this particular region is significant. It's because the first eyes evolved while organisms inhabited underwater environments. This portion of light is transparent in water. Infrared and ultraviolet light, however, render water somewhat opaque. If the first organisms evolved in sulfur lakes on a planet orbiting a neutron star, their eyes might have adapted to see something like X-rays. With that clarified, how does light form, and how does it enable us to perceive color? In the core of the Sun, hydrogen nuclei undergo nuclear fusion due to immense pressure, transforming into alpha particles and emitting gamma radiation. This radiation ricochets around the Sun, colliding with other hydrogen atoms over thousands of years, losing energy in the process, until it ultimately emerges as visible or ultraviolet light. It then reaches Earth. Light can either be absorbed or reflected, depending on the material it encounters. This is determined by the nature of the material. For example, a blue piece of cloth appears blue because it reflects the blue wavelength of light while absorbing all other wavelengths. Thus, it is every color but blue, since blue is reflected and not absorbed. This is why black materials heat up significantly in the sun. They absorb all light and reflect very little. On the other hand, the opposite is true for white. All of this is referred to as bulk reflection and absorption, when a beam of light interacts with many atoms simultaneously. Factors such as the distance between molecules or how the molecules are organized may affect the colors of light reflected. For instance, snow and ice are both composed of the same type of molecules. However, their different arrangements result in snow being white and ice being transparent. Meanwhile, water absorbs minimal light, and most of it passes through. One would need to venture deep into the ocean to avoid seeing sunlight. Similarly, consider carbon organizing its atoms in a lattice results in diamonds, while arranging them in a hexagon produces graphite. So, coming back to our initial question, do atoms possess color? From the perspective of bulk reflection, no. The wavelengths of light are larger than the size of an individual atom. Thus, color only becomes apparent at a larger level. But what about thermal radiation? When you heat something up, the atoms inside start to vigorously collide with each other, releasing photons. Regardless of the substance type, the emitted light will adhere to the same color spectrum. However, once again, this only applies when you have more than one particle. For individual atoms, no color can arise from thermal radiation. Finally, there's gas discharge. By passing electricity through a cloud of atoms, they become excited and release photons. The emission of photons in this scenario can vary in wavelength, resulting in different colors depending on the substance's nature. As a result, each element possesses its emission spectrum. These are the colors emitted by hydrogen atoms, and similar patterns exist for iron and other elements. In conclusion, each chemical element has its distinct color fingerprint defined by its emission spectrum. In a sense, you could consider that as its color. However, in a literal sense, the one we perceive in our everyday life, no, an atom, is physically smaller than the wavelength of light, making color non-existent at the atomic level. There are 4 fundamental forces or interactions in nature: gravity, the weak force, electromagnetism, and the strong force. Gravity is most familiar to us at larger scales, but at the quantum level, the other 3 forces dominate. Electromagnetism is exceptionally stronger than gravity, approximately 10 to the power of 37 times, and is responsible for electron-proton attraction in atoms. The question arises, why don't multiple protons in atomic nuclei repel each other strongly due to the strong electromagnetism? According to Coulomb's law, in a helium atom, the 2 protons experience a repulsive force of about 90 newtons or 20 pounds, which should cause them to fly apart instantly. However, the reason protons remain bound is the presence of the even stronger force called the strong nuclear force, about 100 times stronger than electromagnetism, which operates at the scale of atomic nuclei. This force works differently from electromagnetism and is less familiar to most people, as it is typically not taught at the pre-college level. The fascinating world of quantum chromodynamics reveals how protons and neutrons stay tightly bound within atomic nuclei, resisting the enormous repulsive force of electromagnetism. The strong nuclear force, which is responsible for the binding energy within atomic nuclei, accounts for about 99% of the mass of ordinary objects, contrary to the misconception that the Higgs field is the primary contributor. To understand the strong force, we need to explore the composition of protons and neutrons. They are made of quarks, fundamental matter particles, and gluons, force particles. A proton contains 2 up quarks and 1 down quark, while a neutron has 2 down quarks and 1 up quark. Gluons, responsible for keeping quarks together, carry a color charge, which is analogous to an electric charge, but functions differently and is unrelated to optical colors. The color charge comes in 3 types: red, green, and blue, which combine to make a neutral white. Color charges need to be balanced to create neutral charges, either through a combination of the 3 colors or through color-anticolor charges. Gluons interact with quarks and bind them together. Quarks and gluons are the only particles affected by the strong force, and gluons serve as the force mediators, similar to photons in electromagnetic interactions. If quarks get too far apart, the rubber band breaks, but instead of releasing the quark, the energy required creates a new quark-antiquark pair called a meson. This confinement principle ensures that free quarks cannot exist, and they are always confined with at least one other quark. Mesons play a crucial role in the interaction between protons and neutrons in the nucleus. While the strong nuclear force is weaker than the strong force within nucleons, it is still much stronger than the electromagnetic repulsion between positively charged protons. This force only acts at very short distances, around the diameter of a proton, and diminishes rapidly with greater distances, limiting the size of stable atomic nuclei. In summary, the strong nuclear force, mediated by mesons, keeps protons and neutrons tightly bound together in atomic nuclei. It works in harmony with the strong force that binds quarks within nucleons. This understanding of the strong force is essential for comprehending the nature of matter and the existence of objects and life as we know it. The subatomic realm can be a perplexing place, but you would assume that we've studied atoms long enough to at least comprehend their most fundamental properties. Things like how large a proton is. And based on several experiments, scientists had believed they had a pretty good grasp on it too. However, an ingenious 2010 experiment returned with a very dissimilar number for the size of a proton, challenging what we thought we knew. Now, after nearly a decade of re-examination, scientists believe they've resolved what's known as the proton radius mystery. Before we delve into the details of the latest findings, I must correct the information about atoms. Many of the things you were taught about them in grade school are oversimplified. The proton itself is not a smooth billiard ball, but more like a cloud of quarks held together by gluons. The quarks that compose a proton give it a positive charge, and the threshold of that positive charge can be considered as the proton's size. For decades, scientists have used two approaches to determine the radius of a proton's boundary. One method involves directing electrons at atoms, often hydrogen, which in its simplest form consists of a single proton in the nucleus with one orbiting electron. By observing how the electrons interact with the nucleus, scientists can identify where the proton's positive charge begins to diminish. The other method measures the energy required to excite an atom's electron from one state to the next. And once again, hydrogen is often the preferred atom for this investigation. In its lower energy state, hydrogen's electron doesn't merely orbit around the proton, but actually spends some time within the proton. Your previous assumptions about atoms taught in grade school are indeed inaccurate. Because electrons carry a negative charge, when one is inside the proton's positive charge pulls it in opposing directions, reducing the electrical attraction between them. Consequently, the energy needed to excite the electron to its next energy level is decreased. Thus, the hypothesis suggests that the larger the proton, the more time an electron will reside within it, resulting in weaker atomic binding. By measuring the energy required for an electron inside a proton to transition to the next energy state, scientists can deduce the size of the proton. Over the years, these two methods more or less agreed that the proton's radius was approximately 0.8768 femtometers, and all was well until about a decade ago when someone had the brilliant idea of substituting hydrogen's electron with a muon. Muons are similar to electrons in every aspect, except they are 207 times more massive. That added weight means that the muon spends more time inside the proton, making it switch to a higher energy state, millions of times more sensitive to the proton's size than the electron is in regular hydrogen. By measuring the proton using muonic hydrogen, they came back with a result 4% smaller than the previously accepted size, a difference that's not insignificant. But the sensitivity of the method was too much to ignore. So scientists had a problem. Were their previous measurements off? Or was this a hint at something more tantalizing? Maybe muons and protons interacted in ways that made the protons shrink, or muons somehow behaved differently than electrons. Maybe the discrepancy would reveal some heretofore unknown physics, or even new elementary particles. Which brings us to September of 2019, when scientists at York University in Toronto announced the results of an experiment that used regular, electronic hydrogen like most experiments before. Like those past experiments, they excited the electron into a higher energy state. Only this time, the scientists used a high-precision measuring technique called frequency offset separated oscillatory fields, which they modified for this experiment. Their results showed the proton's radius was right around 0.833 femtometers, consistent with the muonic hydrogen experiment from 2010. So the results are bittersweet. It looks like the discrepancy in the proton's size was just down to measurement error, and not a hint of some undiscovered realm of particle physics. But at least the proton's size is finally settled. If you imagine a table that is 1 billion times larger, its atoms would be the size of melons. But even so, the nucleus at the center would still be far too small to see, and so would the electrons as they dance around it. So why don't our fingers just pass through atoms, and why doesn't light get through the gaps? To explain why, we must look at the electrons. Unfortunately, much of what we are taught at school is simplified. Electrons do not orbit the center of an atom like planets around the sun, as you may have been taught. Instead, think of electrons like a swarm of bees or birds, where the individual motions are too fast to track, but you still see the shape of the overall swarm. In fact, electrons dance. There is no better word for it. But it's not random dancing. It's more like ballroom dancing, where they move in set patterns, following steps laid down by a mathematical equation named after Erwin Schrödinger. These patterns can vary. Some are slow and gentle, like a waltz, whereas some are fast and energetic, like a Charleston. Each electron keeps to the same pattern, but once in a while, it may change to another, as long as no other electron is doing that pattern already. No two electrons in an atom can do the same step. This rule is called the exclusion principle. Although electrons never tire, moving up to a faster step does take energy. And when an electron moves down to a slower pattern, it loses energy which it gives out. So when energy in the form of light falls on an electron, it can absorb some energy and move up to a higher, faster dance pattern. A light beam won't get far through our table, since the electrons in all the atoms are eager to grab some energy from the light. After a very short while, they lose this gained energy, perhaps as light again. Changes in the patterns of absorbed and reflected light give reflections and colors, so we see the table as solid. So why does the table also feel solid? It feels solid because of the dancing electrons. If you touch the table, then the electrons from atoms in your fingers become close to the electrons in the table's atoms. As the electrons in one atom get close enough to the nucleus of the other, the patterns of their dances change. This is because an electron in a low energy level around one nucleus can't do the same around the other. That slot's already taken by one of its own electrons. The newcomer must step into an unoccupied, more energetic role. That energy has to be supplied, not by light this time, but by the force from your probing finger. So pushing just two atoms close to each other takes energy, as all their electrons need to go into unoccupied high-energy states. Trying to push all the table atoms and finger atoms together demands an awful lot of energy, more than your muscles can supply. You feel that as resistance to your finger, which is why and how the table feels solid to your touch. The visible universe is mainly composed of fewer than 100 naturally occurring elements. Nevertheless, this limited set of building blocks, called atoms, gives rise to an astonishing diversity of chemical substances, both in the cosmos and within our own bodies. The reason for this vast array of chemical substances is that atoms rarely exist in isolation. Instead, they predominantly combine with other atoms through chemical bonding, creating an almost limitless array of chemical combinations and materials. These combinations give rise not only to the multitude of phenomena observed in the universe, but also to the complexity necessary for life, energy sources, consciousness, and other macro-scale processes. The universe is not monotonous because atoms form bonds with each other, resulting in rich chemicals with properties fundamentally different from their constituent atoms. This happens because of the role that energy plays in the formation of molecules, rooted in quantum mechanics. Important chemicals in our lives, such as the air we breathe, are composed of molecules rather than individual atoms. Oxygen, for instance, exists as O2, with two oxygen atoms bound together. Similarly, nitrogen is found as N2, and water is H2O, consisting of two hydrogen atoms and one oxygen atom. Atoms predominantly exist as molecules due to their tendency to adopt a state of lowest energy. Just as a marble at the top of a hill will naturally roll down to the bottom, all natural systems seek to minimize their potential energy. This principle also explains the unidirectional flow of rivers from high ground to lower ground. Energy plays a crucial role in the formation of molecules. For instance, when looking at the simplest atom, hydrogen, consisting of one proton and one electron, it is usually found as H2, or hydrogen gas. Quantum mechanics helps explain why atoms form molecules to achieve lower energy states. When a second hydrogen atom is introduced, interesting interactions occur. As the atoms get closer, the electrons, being negatively charged, repel each other, but they also get affected by the positive charge of the protons in the other atom, leading to attraction. There is a balance, or sweet spot distance, where the protons prefer to be, allowing electrons to be shared while minimizing repulsion. The attraction between atoms is not solely due to electron cloud repulsion. Multiple interactions are at play. The system's behavior is governed by the total energy of the system, determining how atoms bond together to form molecules. To determine the lowest energy state of a two-atom system, such as a hydrogen molecule, several factors must be considered, including the kinetic energy of each atom and the potential energy between the protons and electrons. These calculations are encapsulated by the Hamiltonian, representing the energy of the system in quantum mechanics. Solving the time-independent Schrödinger equation using the Hamiltonian yields possible values for energy. However, this equation is not easily solvable and is often represented graphically, showing the energy changes as the two atoms move closer together. At a certain point, the graph exhibits a dip, representing the lowest energy state when the atoms are at an optimal distance from each other. In this optimal state, the two atoms are more content being together at a lower energy level than when they were separate. This is why hydrogen atoms naturally combine to form molecules of H2 rather than remaining isolated. Such electron sharing between atoms is called a covalent bond, and similar covalent bonds form between other atoms. The stability of atoms and their tendency to bond with others are related to the numbers of electrons in their shells around the nucleus. Atoms with specific numbers of electrons, such as 2, 10, 18, 36, 54, or 86, are particularly stable due to the lowest potential energy they possess. These numbers correspond to the electron count of the naturally occurring noble gases, which are chemically inert and do not readily bond with other atoms. Atoms strive to attain a full valence shell of electrons, which involves either sharing electrons through covalent bonds or transferring electrons through ionic bonds. The attractive force for sharing electrons to achieve a full valence shell is balanced by the repulsive forces of electron clouds and protons. The explanation for these magical numbers lies in quantum mechanics, specifically in the Schrödinger equation and the Pauli exclusion principle. The latter states that no two fermions, such as electrons, can occupy the same quantum state, and electrons in the same orbital must have opposite spins. By combining these principles, these specific sequences of numbers are determined as the ones resulting in the lowest potential energy of chemical systems. In complex calculations involving multi-atom systems like water, H2O, approximations like the Morse potential equation are commonly used. These calculations show bond lengths that lead to the lowest potential energy of the molecule. Ultimately, quantum mechanics helps us understand how nature behaves, but it doesn't provide the underlying reason for why nature is as it is. It merely illuminates the workings of nature without explaining the fundamental why. Neutron stars are some of the most extreme entities found in the universe. They appear as colossal atomic nuclei, with diameters stretching over kilometers, and possess mind-boggling density and violence. But how can such a phenomenon possibly exist? The existence of a star is intricately balanced between its gravitational force and the radiation pressure stemming from the fusion reaction occurring at its core. Within a star's core, hydrogen undergoes fusion and transforms into helium. As time passes, the hydrogen supply depletes, and if the star is massive enough, helium begins fusing into carbon. As these massive stars evolve, their cores undergo layering, with progressively heavier atomic nuclei accumulating at the center. Carbon fusion leads to neon, which further transforms into oxygen and silicon. Ultimately, the fusion process reaches iron, an element that cannot undergo further fusion. When the fusion process halts, the radiation pressure diminishes rapidly, causing the star to lose its equilibrium. If the core mass exceeds around 1.4 solar masses, a catastrophic collapse ensues. The outer part of the core accelerates to velocities reaching up to 70,000 kilometers per s as it collapses toward the star's center. At this juncture, only the fundamental forces operating within an atom come into play to counteract the gravitational collapse. The quantum mechanical repulsion between electrons is overpowered, leading electrons and protons to merge into tightly packed neutrons, similar to an atomic nucleus. The outer layers of the star are violently expelled into space during a dramatic supernova explosion. Now, we witness the emergence of a neutron star. Its mass varies between 1 and 3 times that of our Sun, compressed into a compact object with a diameter of approximately 25 kilometers. It contains the equivalent mass of 500,000 Earths within this minuscule sphere, akin to the size of Manhattan. The neutron star's density is so extreme that 1 cubic centimeter of its material holds the same mass as an iron cube spanning 700 meters across. This quantity amounts to roughly 1 billion tons, comparable to Mount Everest's mass, confined within the space of a sugar cube. The gravitational pull of a neutron star is remarkably potent as well. Dropping an object from 1 meter above its surface would cause it to hit the star in 1 microsecond and accelerate to a velocity of 7.2 million kilometers per h. The surface of the neutron star displays exceptional flatness, with irregularities not surpassing 5 millimeters, and it possesses an extremely thin atmosphere of hot plasma. Concerning temperature, the neutron star's surface reaches approximately 1 million Kelvin, contrasting with our Sun's temperature of 5,800 Kelvin. Now let us delve into the inner workings of the neutron star. The crust is incredibly solid and likely composed of an iron atom nuclei lattice, interspersed with a sea of electrons. As we approach the core, The number of neutrons increases while protons decrease, eventually resulting in an immensely dense mixture of indistinguishable neutrons. The cores of neutron stars remain enigmatic and mysterious. Although we haven't fully grasped their properties, the prevailing belief suggests they may consist of superfluid neutron degenerate matter or an ultra-dense quark matter known as quark-gluon plasma. These peculiar states of matter defy conventional understanding and can only thrive in ultra-extreme environments. In many aspects, a neutron star bears a resemblance to a colossal atomic nucleus, distinguished mainly by the forces binding them together. Atomic cores are governed by strong interaction, while neutron stars are governed by gravity. If that weren't already extreme enough, let's explore some other attributes. Neutron stars exhibit incredibly fast rotations, with young ones spinning several times per second. And if a nearby star is unfortunate enough to be captured by the neutron star's gravitational pull, it can accelerate its rotation to several hundred times per second, as seen in the case of PSR G1748-244468, which spins at approximately 252 million kilometers per h. This rapid rotation leads to a peculiar star shape. We designate these objects as pulsars due to their emission of strong radio signals. Additionally, the magnetic field of a neutron star is approximately 8 trillion times stronger than Earth's magnetic field. This magnetic force is so potent that it bends the paths of atoms as they come under its influence. The observable universe, with its vastness, is hard to grasp, and according to certain theories, it may be relatively insignificant. Current calculations indicate that the unobservable universe could be even larger, possibly exceeding 20 trillion light-years in diameter. Despite its enormity, much of it might be empty, similar to the scarcity of observable matter. Matter, composed of countless atoms, is incredibly small, beyond the resolution of our most advanced microscopes. However, scientific evidence confirms the existence of atoms, consisting of subatomic particles like protons, neutrons, electrons, and quarks. Astonishingly, there are theories suggesting that everything, including humans and the entire observable and unobservable universe, could be akin to an atom in a grander reality. One such concept is the one-electron universe theory, suggesting that what we perceive as multiple electrons might stem from just one particle moving swiftly back and forth in time, creating the illusion of many. Although this theory lacks strong scientific support, it serves as a starting point for other similar ideas with more backing. A more mainstream variation is rooted in the multiverse theory, proposing that all atoms, electrons, and properties of matter in our universe could be equivalent to an atom in a larger universe. This idea has been explored in science fiction, where our universe is seen as a mere speck on a higher plane of existence, or where each atom within us contains whole other existences. Infinity plays a vital role in these concepts, suggesting that no matter how vast our universe is, if the multiverse theory holds, there could be infinitely larger universes, making us appear subatomic from their perspective. Observing the universe, we see how minuscule subatomic particles come together to form increasingly larger structures, from celestial objects to complex organisms. This leads to the question of whether the universe itself could be just one part of something even greater. The blurring of micro and macro levels cannot be disregarded until we have a comprehensive theory of everything that unifies quantum and classical physics. According to the popular theory of the universe's creation, it began as an infinitely dense singularity before expanding through the Big Bang, implying that everything we know was once inconceivably small. However, it is important to note that the initial singularity contained the necessary components for the formation of atoms, distinguishing it from an actual atom. Although these ideas challenge our understanding of reality, they serve as thought experiments to contemplate our place in the vast cosmos. While they might be mind-boggling, they do not diminish the wonder and significance of our existence. String theory is considered one of the leading contenders for a theory of everything, aiming to understand the true scale of reality. In this theory, atoms are not depicted as spherical objects, but rather as string-like structures that vibrate, responsible for all interactions in the universe, including the laws of physics, gravity, and quantum mechanics. However, string theory faces challenges, particularly concerning dark energy, which constitutes a significant portion of the universe. Most string theory models struggle to explain the dominance of dark energy compared to observable matter. Some recent attempts have been made to incorporate dark energy into string theory, including a variation proposed by researchers from Uppsala University in Sweden. This variation suggests that our universe exists on the edge of a constantly expanding bubble, where everything we know is merely a small component of something much larger. Inside the bubble and beyond its edge, unknown dimensions might exist, and the infiltration of dark energy from the wider bubble universe could provide a potential explanation. If this version of reality were accurate, it would drastically challenge our current understanding of science. It would place human beings as infinitesimally small parts within a much grander and incomprehensible structure. However, it's essential to recognize that this idea is merely a thought experiment, a fun way to ponder our place in the cosmos. Even if our perspective proves limited and our knowledge flawed, the insignificance from another viewpoint does not necessarily diminish the value of our existence. Since the beginning of human history, over 100 billion people have passed away. So, what happened to all these individuals considering the law of conservation of matter, which states that matter cannot be created or destroyed? Well, their atoms must still exist, right? Interestingly, I'd like to propose that the atoms of your departed loved ones haven't just disappeared, but have actually become an integral part of you, the world around us, and are even embarking on a fascinating journey across the universe at this very moment. Let's delve into this concept and understand how it's possible. The human body is comprised of roughly 60% water, 20% fat, 15% proteins, 2% carbohydrates, and 2% salts and minerals, along with 1% other elements like oxygen gases and vitamins. The majority of the molecules in our bodies take the form of water, H2O. Upon death, this water either evaporates from the body and enters the atmosphere or seeps into the ground. The speed of this process depends on the temperature and environmental conditions to which the body is exposed. Most of the water, even if in liquid form, eventually becomes part of Earth's water cycle, being heated into steam, ascending to the clouds, and eventually returning as rainwater. A considerable portion of this rainwater ends up in rivers, lakes, and eventually, even in our drinking water. Your body utilizes this water for various purposes, such as incorporating it into cells, regulating temperature, and sustaining other bodily functions. Some of the rainwater is absorbed by plants, which is then utilized in photosynthesis, a chemical reaction involving water, carbon dioxide, and sunlight that produces carbohydrates and oxygen. You and other living beings breathe in this oxygen released by plants to sustain life. As for the carbohydrates resulting from water and photosynthesis, they become part of the diet of both you and other animals as you consume fruits and vegetables. Throughout the process of metabolizing these carbohydrates from plants, you produce the very substances essential for plant life, carbon dioxide and water, creating a continuous cycle. Having clarified what happens to the H2O in your body, let's explore what becomes of your soft tissues, composed of carbohydrates, fats, and proteins. These tissues undergo metabolism with the help of approximately 100 trillion bacteria residing in your body. Curiously, these bacteria have been with you all along, mainly in your gut. Your body's robust immune system normally keeps these countless bacteria in check. However, upon death, your immune system ceases to function, giving these bacteria the opportunity to consume the tissues in your body. As these bacteria metabolize your soft tissues, they use them for energy and reproduction. This process could be likened to a slow burn, as the molecules digested by the bacteria eventually transform into water and carbon dioxide, identical molecules formed through burning. Additionally, other gases, such as nitrogen oxides and ammonia, are produced from proteins in your body. Remarkably, these gases are potent greenhouse gases, with nitrogen oxides being approximately 300 times more potent than carbon dioxide in the atmosphere. As the bacteria continue metabolizing and oxygen becomes scarce, anaerobic bacteria take over. These bacteria do not require oxygen to metabolize your tissues, but generate methane, hydrogen sulfide, and ammonia as byproducts, which are known for their unpleasant odors and are also potent greenhouse gases. Eventually, these substances exit the body and integrate into the atmosphere. Therefore, when you step outside and detect an unusual scent in the air, there's a chance that you're inhaling atoms originating from your great-grandmother. Additional atoms and molecules within your body are released as nutrients into the underlying soil. For each kilogram of dry body mass, around 32 grams of nitrogen, 10 grams of phosphorus, 4 grams of potassium, and a gram of magnesium are ultimately contributed to the soil. Interestingly, these components serve as fertilizers for the plants in the vicinity of the burial site. Overall, the decomposition process plays a positive role in the surrounding ecosystem. Now, let's consider cremation. What occurs after your body undergoes cremation? The majority of atoms in your body, hydrogen, carbon, nitrogen, oxygen, and sulfur, are converted into gases due to the intense heat of the cremation process. These gases are released into the atmosphere in the forms of water vapor, carbon dioxide, nitrogen oxides, and sulfur oxides. However, it's worth noting that a significant portion of your remains, several kilograms, takes on the form of ash following cremation. Interestingly, the weight of these ashes is approximately equivalent to your birth weight. Hence, in a somewhat ironic twist, your departure from this world parallels your initial entry in terms of mass, showcasing the cyclical nature of life. So, what is the composition of these ashes? An analysis reveals that phosphate and calcium constitute the bulk of these ashes, which is understandable given that these elements form the structure of your bones. Consequently, these atoms primarily originate from your skeletal framework. What becomes of these ashes? They are likely to eventually find their way into the soil, becoming integrated into the structure of plants. Subsequently, these plants may serve as nourishment for animals and humans, ultimately returning the remnants of your existence to human bodies. Small fragments of you could end up in your great-grandchildren's morning cereal or burger, allowing you to persist in the sustenance of life on our planet. However, there exists a noteworthy exception. Your body contains trace amounts of radioactive elements. Some of these elements will undergo spontaneous fission through radioactive decay, transforming into other elements before entering the biosphere. For instance, radioactive potassium may transition into calcium, while minute quantities of thorium and uranium within your body will eventually evolve into lead. Alongside this decay process, certain helium atoms will also be generated. Due to the insufficient gravitational force on our planet, helium tends to escape into space. While a fraction of this helium may be captured by massive bodies like the Sun and Jupiter, a portion will venture beyond the solar system, drifting toward the stars and into the cosmos. Consequently, certain atoms from your composition are destined for a remarkable voyage, indefinitely traversing the farthest reaches of the universe until the end of time. Even though life on Earth might seem quite constant and predictable with the ebb and flow of tides, the daily cycle of the Sun, and the unchanging progression of months, when we consider the larger picture, our universe is truly full of dynamic changes and activity. Every day, millions of stars are born and die, and eventually, the same fate awaits our own Sun. Billions of years from now, as our star begins to transition into a red giant, temperatures on Earth will increase, leading to the extinction of life. Just a few billion years after that, once the Sun exhausts its nuclear fusion fuel, it will begin its death throes. During this process, it will shed its outer layers and eventually fade into darkness. Nothing in our universe is truly eternal, or is it? Atoms are the fundamental building blocks of matter. They make up our universe as we know it. When we die, our bodies do not simply disappear. Instead, they break down into their constituent parts and become part of the ecosystem again. In essence, our atoms continue to exist long after we are gone. But how long can atoms last? Will they eventually cease to exist? To answer this question, we need to understand a bit about how atoms function. As you may know, atoms consist of protons and neutrons, surrounded by a cloud of electrons. The number of electrons in the cloud is equal to the number of protons, which contributes to stability. Ultimately, the number of protons determines the atomic number. For example, helium has 2 protons, giving it an atomic number of 2, and it appears as the second element on the periodic table of elements. The number of neutrons in an atom is generally constant, but not always. Sometimes, if an atom doesn't have the correct number of neutrons, it may lose a neutron, similar to losing a sock in the wash. When this occurs, the atom becomes unstable, and in an effort to become stable, it emits subatomic particles. Often the atom will release an electron. This is how atoms undergo changes. Whenever you have a heavy atom, there is a chance that it will spontaneously begin to break down into smaller particles. This process is known as radioactive decay. It is a fundamentally random process, meaning we cannot precisely predict when a breakdown will occur or when a subatomic particle will be emitted. However, We can analyze the pattern statistically and estimate the average time it takes for half of the atoms in a sample to decay, which is called the half-life. As atoms have a finite number of protons and neutrons, they will generally emit particles until they reach a point where their half-life is so long that they are effectively stable. For example, bismuth-209 is believed to have the longest decay rate. It undergoes alpha decay, and its half-life is over 1 billion times longer than the current estimated age of the universe. So, for practical purposes, bismuth-209 is considered almost eternal. However, true eternal life would depend on whether protons can decay. Some scientists have proposed hypotheses related to this, known as proton decay, a hypothetical form of radioactive decay. According to one idea, the Georgi-Glashow model, protons can transition into a positron and a neutral pion, which then decays into 2 gamma-ray photons. The estimated half-life for protons in this model is 1.29 times 10 to the power of 34 years. This is an extremely long time. However, currently, there is no experimental evidence to confirm proton decay. Nevertheless, ongoing research at some of the world's major laboratories may, with luck and scientific rigor, reveal new insights in the future.